this time, I would like to ask our next speaker to please come and set up. We have heard quite a bit about this final speaker throughout the day, tormenting John with those on samples. And I believe he will continue to do so today. So unintentionally, you are also responsible for my undergraduate work with John, because he made me also figure out what some of the terms that he was using were. My term was Har-random matrix. Johnny had already figured out the permanent thing.
It just means random matrix. It's a mathier way to say that.
So with all that being said,
Okay.
Scott Aaronson for the final talk of the conference.
Thanks.
John likes to call it a hardy har matrix.
A hardy har. All right. Well, what happened to the image? Yeah. Okay. Thanks everyone for staying until the end of the workshop, and also thank you to the staff here of this conference center for duct taping my glasses when they snapped this morning. I probably would not be here giving this talk otherwise. So, so let's see.
So I have to point out a mistake.
What?
The year. We're in 2022.
Yes, that's correct. That's correct. I was updating some old slides, and okay. Thank you. Thank you. That's correct. Okay. So speaking of, yeah. So this is from this photo is from March 2020. This is the last time that I was here in Baton Rouge, and it was the last time that I saw John. Although of course, I had no idea at the time. I was here to give this Hearn lecture. So this is, that's John making the UT Austin Hookem sign, and Jorge Pullen, and we had what?
It's Vulcan.
Oh, yes, you're right. Well, yeah, he made the Hookem on a different occasions. Yeah, you're right. Yeah, and there you are. Okay. You can explain to me exactly what you're doing, so I don't get it wrong. And there's the Cuba license plate. So this trip almost did not happen. As I said, it was March 2020. Everything was being canceled left and right because of this new virus was spreading around, and it did not seem like a good idea to be flying on planes or in airports, and so I said maybe not, and so then I don't know if you can read these, but I was inspired by this morning's talk to go and find the emails, which are some of the last emails that I exchanged with John, basically saying, well, why don't you just get one of your students to drive you there, right? And, because I'm a terrible distracted driver, so I could have stopped driving, right? Which was an issue. So I said that's a good idea. So I asked my group and my postdoc, my then postdoc, Andrea Rochetto, was very happy to go, and so we had this sort of extremely memorable trip. We stopped and saw some alligators. We visited the LIGO, which was just shutting down because of COVID, but was still open. And John was John, right? Like at the we were at a restaurant. He had an incredibly detailed discourse with the waitress about about all kinds of topics, right? But they started playing the piano just louder and louder to try to drown out his voice. And I had no intimation that there was any issue at all with his health. And that was just a few months later. Okay, so but now John, as you all know, he strongly believed in telling things like they are, in in being blunt. So, inspired by, especially, like some of the conversations that I just had with his brother at this meeting, right? I think that in the business world, people get this impression about quantum computing where things are accepted as conventional wisdom among, the people who, make decisions about quantum computing that are just not true. Right, and it's not controversial. It's just within the research community we know that they're not true, and yet somehow when you try to say the reality, like you sound like a crackpot because it's it's going against what all the popular articles repeat. So here would be my like one slide that I would want to convey to calibrate to reality. Someone from the outside who is learning about quantum computing. That the quantum computers it was a remarkable discovery that they can give exponential speedups over any known classical algorithm. But these speedups tend to be very specialized in nature. Okay, they tend to be for some very, very structured problems with the right kind of structure that we can choreograph a pattern of constructive and destructive interference that will concentrate all the amplitude on the right answer and do it faster than a classical algorithm could have done the same thing. A famous example is breaking public key crypto systems, at least the ones that we use today. That's Shor's algorithm. Simulating quantum mechanics, that was Feynman's original dream, and that's maybe the most important economic application of quantum computers that we know about even today. Okay. Now there is also Grover's algorithm and all of the other algorithms inspired by it, which promise more modest speedups, square root or polynomial speedups for a huge range of problems, including just about anything that the business people are excited about, optimization, finance, supply chains, machine learning. Okay, but because the speedup is only quadratic, and it is fighting against the enormous overhead of quantum fault tolerance in order to see any advantage at all. And it is probably, the numerical estimates that people have done are quite scary, right? It's probably quite a long time in the future before that becomes a net win. Okay, and then the most important part, exponential speedups for optimization, for finance, for machine learning on near-term devices. In other words, the claims that, billions of dollars have now been raised for, from startups. I think that in the research community, we have no evidence for any of this. The best that we can say is that we can't prove that it's impossible. Okay, and in general, quantum computing is not a logical continuation of Moore's law. It's not just like the next faster computer, as all of the pointy-haired bosses want it to be. It is a new thing that needs to be understood on its own terms. And so to borrow John's phrase, Schrodinger's killer app, might be something that just hasn't been discovered yet, even though we're now 30 years into this. Okay, so the two important points that I would think of as the hammer of hype. First of all, it is not enough that you just create a superposition over the answers, as banal as that might sound, right? You need to do something involving minus signs, if you want any quantum advantage. You need interference to boost the amplitudes of the right answers and to cancel out the amplitudes of the wrong ones. And secondly, it is not enough, or you could say it is not in itself interesting to do something quantumly. The fact that like again and again, I will make these sort of obvious points that I'm making now, and people will say, but what about this company that did this with a quantum computer? And I will say, but did they beat what you could have done with a classical computer? And then they'll say, well, surely they must have, or they wouldn't be all be talking about it. And I say, let me ask again. Did they beat what you can do with a classical computer, right? And then you look at it, and very often the answer is no, they did not. and what's really crucial here is that the classical side gets to fight back, right? So you don't get to do a comparison against, like the most naive classical algorithm, and then claim a victory if you were faster. You have to publish exactly what problem you are solving and let people who are actually motivated to beat you, try to do as well as they can, at reproducing the results classically. Only if they fail to do that can you sort of claim a robust quantum advantage. Okay, so this brings me to, the, I guess, now controversial term, or so you could say I put it in scare quotes of quantum supremacy. This was what this is, by the way, this is not what Alex Arkhipov and I called it. This is what John Preskill called it a year later. But what he meant by that term is what sort of I would have regarded for since the very beginning as just maybe the number one, the most exciting to me goal of quantum computing. Okay, and this is to disprove the people who say that quantum computing is impossible. Okay, your Gil Kalai, your Stephen Wolfram, right? Your Leonid Levin, your Bob Laughlin, right? There are many people who just take it as obvious that quantum mechanics is just something that people made up that works for a few particles or something, or but who is to say that it's going to work like that when you scale to more particles, right? And for some people they would say it is just an axiom that the universe can be efficiently simulated by a classical computer. If quantum mechanics conflicts with that axiom, then so much the worse for quantum mechanics. Okay. Now to me that seems kind of ridiculous, but I can't prove that it's wrong, right? Ultimately, it's a question that can only be settled by experiment. And so how could we disprove the skeptics of quantum computing? Which I think is even if there were no applications, right? Even if this were purely a scientific endeavor, this would be at least as worth doing as building LIGO, building LHC, building, the James Webb Space Telescope, right? Which were each, these, 10, multi-billion-dollar endeavors, right? And so, we shouldn't lose sight of that. That like the case for trying to build a quantum computer would be overwhelming, even if there were zero applications. Okay, the fact that there are is kind of icing on the cake. Okay. But now since 1994, of course, the sort of gold standard for how do you convince a skeptic that you really have a quantum computer has been Shor's factoring algorithm, right? You just, you say, give me your 10,000 digit number, your composite number, I will give you back the factors. Okay, and that doesn't prove that you have a quantum computer, but it proves that either you have a quantum computer or you have an equally astounding breakthrough in classical algorithms, right? So it's pretty good, right? And of course, this is what made much of the wider world interested in quantum computing. Okay, but then people ask more about it, and they say, well, wait a minute, what does it actually take to implement Shor's algorithm? Oh, you need these fault-tolerant qubits. And okay, so when you say a few thousand qubits, you mean a few thousand logical qubits. And each logical qubit takes a few thousand physical qubits to implement it. So now you're talking a few million qubits, maybe 100 million to be safe. And now you're talking about a whole building, filled with dilution refrigerators. Oh, that sounds kind of scary, right? Like, maybe eventually we'll see that, or maybe we'll wait for someone to have a new idea that gets around the need for this. What can we do in the meantime? Can we disprove at least disprove the quantum computing skeptics in the meantime? Forget for now about doing something useful. Okay, so the suggestion that Alex Arkhipov and I made in 2011, and you've already heard about it in several of the talks today, was to stop sort of obsessing about computational problems with a single right answer. Like, what are the prime factors of this number? Or, what is the rate of this chemical reaction? Or things like that. And, there are broader things that still count as computational tasks. Okay, an example would be, I describe to you mathematically a probability distribution, and now I ask you to output samples from that distribution. Okay, this is what we call a sampling problem. And it turns, maybe this was not obvious a priori, but it turns out that once you switch attention to sampling tasks, it is somehow much, much easier to see the advantages of quantum computers over classical ones. Okay, you can do it based on sort of much more generic complexity assumptions. And you can do it, using devices that are much more rudimentary. Okay, that are not necessarily universal quantum computers, right? That might fall short of that. Somehow you can use tasks that are, in the boson sampling paper, we compared it to, instead of like trying to teach a dolphin to do arithmetic, you just kind of watch the dolphin, in the ocean, interacting with other dolphins and so forth, right? And Shor's algorithm is like, with heroic effort, you teach the dolphin to add integers. Okay, boson sampling is like you watch the dolphin do what it does, and it's already pretty smart, right? So the idea of boson sampling, this was a model of a sort of a subset of quantum computation, if you like, that is almost certainly not universal for quantum computing. For that matter, not even universal for classical computing, right? I don't know how to do, compute the AND of 2 bits, okay, within the boson sampling model, okay? That is how limited it is, okay? But it seems able to solve certain sampling tasks that we that we cannot solve by any efficient classical algorithm. Okay, so what you're allowed to do in this model is basically just you can have a network of linear optical elements, beam splitters and phase shifters, and usually when I give this talk, I give it to computer scientists, and I have to very carefully explain what all of this is, and then I can just assume that they know what is sharp P and BPP to the NP and so forth. But for this audience, I'm going to assume that you know what beam splitters and phase shifters are. Okay, so you can build a network, a passive linear optical network. You can generate a bunch of single photons. In our original proposal, it was in Fock states, and you send them through the network. And then in each output mode, you can have a detector. You can measure how many photons are there. That's it. Okay, those are all the resources that we assume. And so you could think of like in terms of the last talk, to do universal quantum computation based on photonics, following the seminal work 20 years ago of Knolla, Flom, and Milburn, right? You take those resources plus one more, which is the ability to do adaptive measurements. Okay, to measure, the number of photons in a mode and then change what you're doing to the other modes depending on the outcome. We do not assume that ability, right? That's what sort of prevents boson sampling from being universal. But maybe what came as a surprise to some people in the optics world was that even then you still seem able to solve some classically hard sampling task. Okay, and so now we come to the question, well, why? Why is this hard for a classical computer to simulate? And now we get to my blog debate with John Dowling from I guess 2013, right, which you saw this morning. Reprinted. I was just reminded about it. I put the word debate in quotes here, because it wasn't actually a debate. It was more just like, John had to be educated about about how this works. Okay, but what their original papers had said was that, well, you know, boson sampling, you know, is hard for a classical computer to simulate because it involves exponentially many possible outputs. Okay, and it's true that you do have exponentially many, you know, possibilities. You have exponentially many basis states, you know, in your Fock space, right? You know, different sets of lists of occupation numbers of all your bosonic modes. You know, ways of arranging all these photons. Okay, but that in itself does not mean that the problem is hard for a classical computer, right? And one very easy way to see this is to just look at the analogous problem, but with fermions instead of bosons, okay? And that problem turns out to be easy for a classical computer. You know, a classical randomized algorithm can efficiently sample from the probability distribution over a bunch of fermions that would pass through a beam splitter network, okay, but not bosons. Okay, so it's not about, you know, the number of outputs. It's not about, you know, each amplitude being a sum of exponentially many contributions even, okay? But both of those are true for fermion sampling. It really is specifically about the properties of the amplitudes as functions of matrices, okay? So, and the key is that when you have a bunch of identical bosons, then their amplitude to get from some input state to an output state is representable by the permanent of an n, you know, of an n by n matrix if there are n bosons. For fermions, it's the same except it's the determinant. So you put this minus sign into the sum. Okay. So yeah. So here's for some fermions in this table. Here's some bosons. That's the sum. Okay. You know, intuitively, this is because, you know, we have to sum, sorry, this is not showing up right, but you have to sum over all n factorial ways that the n particles could be permuted in going from the initial state to the final state. Each of those permutations contributes a term to the total, and the difference is that if it's fermions, then you have to multiply by -1 whenever two of them get swapped. Okay, and so now these are very famous functions in computer science for reasons having nothing to do with physics. You know, and in particular, you know, one of the sort of algebraic version of the P versus NP problem just is the conjecture that the permanent is much, much harder to compute than the determinant is. Okay, so the determinant, we know fast ways to compute it, such as Gaussian elimination, right? Just diagonalize your matrix. Okay, the permanent was famously shown by Valiant in 1979 to be what's called sharp P complete, which just means sort of as hard as any combinatorial counting problem that you like. Okay, so somehow this minus sign makes that dramatic difference, and somehow, you know, this sharp P completeness of the permanent. This is what we were exploiting in boson sampling. Okay, now to clarify, this does not mean that when we do boson sampling that we solve a sharp P complete problem, right? That would be too good to be true. Okay, that would be, you know, if I were saying that, that would be 100 times worse than the hype that I was decrying earlier. Okay, you know, what we do is we give an argument where we leverage the sharp P completeness of calculating the amplitudes in order to get some kind of hardness for sampling according to those amplitudes. Okay, so you know if you know these amplitudes are exponentially small, right? So even with a quantum computer, it's not like you get to estimate a specific amplitude of your choice. That's what you would need in order to solve a sharp P complete problem, right? And you know what nature lets you do is something weaker than that. It lets you sample a random output with probability equal to the squared absolute value of its amplitude, right? So you get to sort of, as it were, sample a random matrix, but in a way that is biased toward matrices that have larger permanence. Okay, but then, you know, the new contribution in our work was to say that even that is hard, sort of for reasons related to the fact that the permanent is sharp P complete. Okay, so that was what, you know, John, I think, you know, did eventually understand, and he played a very big role in, you know, helping the, you know, the rest of, you know, the optics community, you know, sort of understand what was going on here. Okay, so now quantum supremacy via sampling problem was, at least claimed to be achieved just a few years ago by the group at Google using their Sycamore chip. Okay, so the first claim of quantum supremacy was not based on boson sampling. Okay, they considered doing boson sampling, but they around 2015, I was involved in the discussions with Google, and the team of John Martinez decided to just sort of take boson sampling and adapt it to their hardware. Okay, do an analog of it for superconducting qubits, on a chip. And they said, all right, we're going to leave it to you to adapt the theory of boson sampling to this different setup. And we said, okay, we'll do that. That seems cheaper than, whatever $100 million it would take to change your experiment. So they sampled from this distribution over 53-bit strings, where, as far as we know, to sample it classically would take something like 2 to the 53 time. You can do a little bit better using, tensor network methods, for example. And there is a lot of back and forth debate right now about, just how quickly can a classical computer spoof this. It seems like, there is some advantage to using the quantum computer. But certainly it's a lot less than Google originally thought. And, there is, I would love to see better quantum supremacy experiments that make, the quantum advantage, a lot clearer. Okay, in a little bit more detail, sort of the sort of important point about these kind of sampling experiments is, well, you can sort of apply, let's say, a random sequence of gates to your qubits, analogous to the random sequence of beam splitters that we suggested to apply in boson sampling. And then you can measure all of your qubits. This gives you a distribution for a sample from distribution over n-bit strings. Okay, but then there's a really, really crucial question remaining, which is once you have these samples, how do you verify them? Right? How do you know whether the quantum computer was doing the right thing or not? Okay, so what Google did, was about the simplest thing you could think of, and the simplest thing that we could suggest for them to do, which was just take all of these observed outputs, I'm calling these S1 up to SK, and just calculate, use brute force on your classical computer to calculate what would have been the probabilities of these strings being output by an ideal version of the quantum computer. Okay, so calculate these squared matrix elements, and then just add them all up. And if that sum is large enough, then we'll consider the test to have passed. Right, and what we're relying on here is that not all of the output strings are equally likely. Right, some of them have a little bit more constructive interference in their amplitudes. Others suffer a little bit more destructive interference. And if your experiment is working correctly, then you should be preferentially sampling the strings that have the higher amplitudes. Right, so that is what we're doing statistics to check. Okay, we don't have nearly enough samples to sort of reconstruct the entire distribution. Right, we can't calculate the entire histogram. Okay, that's completely out. Right, we can just do this little statistical check with the samples that we do see. Okay, and this is what Google called the linear cross entropy benchmark, or LXEB. Okay, and then the theoretical question that we and others thought about was, well, then how hard is it for a classical computer to just do anything that would spoof this benchmark? Just produce samples that get a high score on that. Okay, so then what happened next was that the group of Chaoyang Liu, who you heard from this morning at USTC in China, pushed forward with a version of boson sampling, what's called Gauss. It's just the version of boson sampling with Gaussian states as the inputs instead of Fock states. So a GBS it's called, and then they did a second demonstration of sampling-based quantum supremacy. First with 50 photons, and in their latest version, they've got more than 100 photons on average. Okay, so this was the second quantum supremacy demo, the first one using photonics. It has a much larger Hilbert space than the Google experiment, okay, which does help in ruling out certain types of attacks, like the one that IBM proposed against Google. But as I just told you before, the dimension of the Hilbert space is not the sort of any assurance of the hardness of the problem, right? So this is kind of necessary but not sufficient. And a key question about the USTC experiment has been, well, how well does it evade other forms of classical spoofing? Okay, so there's been a big debate about this. And basically what the USDC paper says is that if you look at like 7-mode correlations, you can see a non-trivial signal that looks right. And if you extrapolate from that, it looks like if you could measure the 19-mode correlations, which you can't because it would take too long, then you would see a signal there, although the amount of signal decays exponentially with the number of modes. The 7-mode correlations are easy to reproduce on your laptop. The 19-mode correlations, if you believe that they're really there, would not be. Okay, so is this quantum supremacy or is it not? Well, it depends on how you define it. Okay, so so now Google had a response to so like the different quantum supremacists or whatever you call them are kind of fighting each other, right? But they said if you define the boson sampling task to be getting a good linear cross entropy score, for example, or a distribution that's close to the correct one, then they could give a fast classical spoofing algorithm that does better than the hardware, just by beating the hardware on the 1 and 2 mode correlations and taking advantage of the fact that the experiment is has these calibration errors. Like the beam splitter angles are off by 1 or 2%. So that's a little disappointing. It means you have to sort of change the definition of the task if you want to say that there's quantum supremacy here. Okay, so I think there's a great challenge of verifiable BS. BS, of course, meaning boson sampling. I thought that this was corny enough that John would have appreciated it. So wouldn't it be awesome if when designing a beam splitter network, we could smuggle in a single output state with overwhelmingly large probability, one that we knew but that someone else could learn only by running the experiment. Alas, I and a mathematician, Hui Wen, and then Berkowitz and Devlin proved a sort of no-go theorem for this. Proved that the submatrix corresponding to the likely output is just going to stick out like a sore thumb, and a classical computer could find it too. But still, couldn't we secretly boost the probabilities of some huge number of known output states? This is an open problem. I think one of the most interesting open problems in the whole subject. So, could there be applications of boson sampling? You may have seen claims that it can be used to find dense subgraphs or to do molecular vibronic spectra. Unfortunately, I am not convinced that any of this gives real speed-ups over a classical computer, basically because you've got to compete against classical algorithms, such as those of Leonid Gurvitz. More plausible is that you could use boson sampling for generating cryptographically certified random bits. I don't know how useful that is, but that's the closest thing to an application of boson sampling that I currently know about. That would actually rely on having a non-classical device. So the future of boson sampling. Experimentally, we would like lower loss, better calibration, more modes. I would like a theory that explains what is the best possible classical spoofing attack against linear cross entropy or other benchmarks for boson sampling. We have that for random circuit sampling, right? But not for boson sampling. I'd like to justify the classical hardness of boson sampling by proving, that the permanence of random matrices are sharp p hard to approximate. That was a central question that Alex Arkhipov and I left open, and it's still open. Is the classical hardness preserved if a constant fraction of the photons get lost? As they do in the experiments, like of USTC. And then can you figure out an actual application of boson sampling, or at least a fast way to verify the results? I was going to add, and can you explain the, why boson sampling is hard with no mention of complexity theory, in honor of John, but I decided to leave that one out because I really don't think so. So that's all. Thanks for listening. Yeah.
Thanks for your talk.
Yeah.
Really liked it.
Thanks.
I'm curious, just I guess from personal perspective, when did you first have this idea to go to sampling tasks, and what made you think of that?
Yeah, that's a great question. So it came out of the work that I was doing on trying to get an oracle separation between BQP and the polynomial hierarchy. Okay, that's where it came from, right? This was one of the biggest problems in quantum complexity theory, right? I failed to solve it. I was able to sort of give some ideas which were later used by Ron Raz and Avishai Tal, who finally solved that problem in 2018. Okay, but at the time, when I was working on this, it was like 2008, 2009, around then, and what I noticed was that I could prove the separation between BQP and the polynomial hierarchy if I was allowed to look at sampling problems. Okay, and it just sort of popped out of just the nature of the problem that if I take a random Boolean function, then a quantum computer can easily sample from its Fourier distribution. Right, and you can just very easily argue that no classical constant depth circuit will be able to keep track of what's going on because it would have to solve these Sharp-P complete problems basically. Do these exponential sums. Right, and then that made me wonder, well, is there some version of this but not needing an oracle? Is there some real-world version of this? Right, and this is very much analogous to how Shor's algorithm was discovered. Right, it started with these abstract, nerdy oracle results. Simon's algorithm, for example, right, which actually got rejected, from the main theory conference because people said, who cares about oracles, right? But one guy on the program committee really liked Simon's paper. His name was Peter Shor, right? He said, well, obviously, if you just change the problem a little bit, to modular exponentiation, right, you could get something that didn't require an oracle, and that in fact would let you factor integers. Okay, so I said, could we do something like that? Could we instantiate this sampling task by something real? And then I realized that, okay, you're going to want not just a Sharp-P complete problem, which would be easy to do, but sort of a robustly Sharp-P complete problem. Because what you're going to need is that the amplitudes, it should not just be hard for a classical computer to sample exactly the same distribution, right? It has to be hard for it even to sample approximately the same distribution, right? And that requires problems that are sort of Sharp-P complete even to approximate and even on average. Right? And what could do that? Well, at least, for the permanent, we at least knew, a lot of robustness properties. Right, not quite what was needed, but so then being a complexity theorist, I knew that about the permanent, and so then the question is, what kind of quantum computation will make the permanent show up in amplitudes? And then I remembered what Barbara Turhall had told me once, right, that bosons somehow involve the permanent, and actually Avi Wigderson had also told me this, right? So I had that in the back of my mind. I never understood it. And then Alex Arkhipov was looking for a summer project. And I said, and he said, he likes the permanent, wants something about the permanent. I said, you know what, I have something. Let's think about this. So that was how it happened.
So I saw 2 questions, one here, one here, and then some in the back.
Okay.
Yeah. So mine is a simple question.
Yeah.
What advantage does the boson sampling have over fermion sampling?
So fermion sampling, you can simulate it easily with a classical computer. That's the short answer to your question. So fermion sampling, is just out as a way to demonstrate quantum supremacy, right? It can't work for that. And the way that the classical simulation works is actually, it's a little bit non-trivial, but it's ultimately relying on the fact that the determinant has a fast classical algorithm. Right?
Whereas the boson sampling doesn't, so it will be a better proof for a quantum computer?
Not just better, but a demonstration at all of any quantum advantage, which you would not get with non-interacting fermions.
Thank you.
Yeah.
Okay.
Yeah, so thank you for your talk.
Yeah.
So in 100 years,
Mm.
say, the history of science will say like in 2000 something, so and so demonstrated quantum supremacy, right? The question is, and you kind of touched on this, but I would like your perspective on it.
Yeah.
Will we actually recognize it when we see it?
Yeah, well, so this is a question. I mean, I think like with, there are some milestones, like, like the first person walking on the moon, where it's very discrete, when it has been achieved, right? Then there are other things, like, when does voice recognition become a useful technology, right? Where, it's more of a sigmoid, right? It's more of, there was a time, let's say, in the 1980s, voice recognition was obviously not useful, right? Now it obviously is, right? But, like at what day did it change, right? Well, there's no, there's this, a decade or more when it just became more and more useful, right? So, quantum supremacy is a little bit of a fuzzy milestone, right? Because it depends on what do we count, what kind of tasks are we allowed to consider, right? Like how do we even measure the resources use of the classical algorithm, right? Let's say the classical computer can be just as fast as the quantum computer, but you need 100,000 cores working in parallel, as opposed to the quantum computer that just needed the one chip, right? And so then the classical computer is winning on cost. The quantum computer is actually winning on carbon footprint, right? Ironically, even though it needs this dilution refrigerator, right? It's still winning. Okay, so so who wins, right? We're now in the era where you have to kind of squint, and the hope is that eventually we'll get to the other end of the sigmoid. We'll be in the era where the quantum advantages, at least for these kinds of benchmarks, are so obvious that you don't have to squint anymore. And I would like to see that, and then we would like to see obvious quantum advantages for tasks that are additionally useful. Right, but in some sense, you could think of these, as sort of demonstrations of like, if this is how hard it is to get a clear quantum advantage for a completely artificial benchmark, right? Then that calibrates you when someone is saying, oh, I can solve, I can help Volkswagen, with its, vehicle routing, like right now with a quantum computer, right?
So we had a question here, and then I don't want to hold us up too long for the outro, so I would probably ask anyone else to.
Okay.
So briefly,
Yeah.
following on some of the previous
Yeah,
questions.
sure.
I think everyone in this room understands, just from an applied mathematics perspective, how important the determinant is, right? In all these problems of linear algebra. Even if we don't use it directly,
Yep.
it's foundational. What are there corresponding problems of classical mathematics in which the permanent plays such a role? And the question is, how much analysis has
Yep.
gone into it
Yeah.
compared to those of the
Yeah, so the answer is yes, there absolutely are. I mean, the permanent has been studied since the 1800s, right, by mathematicians. And, so it tends to show up in combinatorics, in statistics. Okay, one example is if you have a bipartite graph, right, then, the way, like, if you look at the permanent of the adjacency matrix of that graph, then that just counts the number of perfect matchings in the graph, right? So it's a way to count matchings in graphs, right? So that's one very important interpretation of the permanent. Okay, but it also it plays an important role in representation theory and in invariant theory. It is not nearly as ubiquitous as the determinant is, right? And in some sense, the reason for that is that, well, it's so much harder to calculate, right? The sort of
this P-sharp
sharp P, yeah.
equivalence that you mentioned, that was a fundamental discovery.
It was,
of the
yeah.
complexity.
It was, yeah. Yeah, but I mean, the determinant, you could say, it is efficiently computable because it is just the product of the eigenvalues. It's the volume of the parallelepiped that's spanned by the rows, which means that it has this clear geometric interpretation. And in some sense, the permanent cannot have an equally simple geometric interpretation, because if it did, then it would lead to a fast algorithm to compute it.
Okay, And with that, I think we're out of time for questions, but let us please thank our speakers.